Let's do one good example problem here which exemplifies how to obtain the important physical quantities in an LC circuit. So here we have it, the 25 microfarad capacitor, a 10 millihenry coil. There's two switches, S1 and S2. So what we're going to do is figure out the period and frequency of the oscillation, and then at the particular time of 1.2 milliseconds, after switch S2 is closed, so backing up, switch S1 is closed, it charges the capacitor. Switch S1 is open, followed by S2 closing, and 1.2 milliseconds later, what is the charge and on the capacitor, and what's the current in the circuit? So that's what our goal is. So from energy, we have the magnetic energy plus the capacitor energy equals the maximum amount of capacitor energy, and that gives us I is square root of 1 over LC square root of Q squared minus little q squared. So we covered that already. From the energy equation we get this. We also had that omega is 2 pi f, which is 2 pi over period, which is square root of 1 over LC. And that is 2,000 radians per second when we plug in the numbers, L and C, 1 over square root. Okay, so frequency is omega over 2 pi. That gives us 320 hertz. And then it's a simple matter to get the period. It's just 1 over the frequency, which is 3.1 milliseconds. There we go. Now, what's Q of 1.2 milliseconds and I of 1.2 milliseconds? Well, Q is capacitance times the EMF. That's the maximum Q in the capacitor. 300 volts times the capacity. That'll be the charge. That gives us 7.5 millicoulombs. Little q is, from our discussion previously, big Q cosine omega t. And if you're confused about sine or cosine, realize that t is equal to 0. We have maximum charge on the capacitor. So when this t is 0, cosine of 0 is 1, yes, maximum Q. So it's 0.0075, 7.5 millicoulombs, cosine omega t, and that's cosine of 2.4 radians. Omega, 2,000 radians per second, t, 1.2 milliseconds, 2.4 radians, minus 5.5 millicoulombs, which indicates that it's charging the other way at that point. Moreover, the current is just the derivative, minus omega q sine omega t, minus omega q sine of omega t, gives us minus 10 amps. So the current at 1.2 milliseconds is flowing the opposite way. That happens to be at that part of its cycle. And that is also a very large current. Nevertheless, that is an application of some of the equations for an LC circuit and how we can find out some of the properties of the circuit. Let's now discuss the last topic, the RLC circuit. So we have resistor, inductor, and capacitor. So we now know that we have an oscillating system. We're going to swing this over here to charge the capacitor and then swing it back, and we start oscillating back and forth. So let's do a basic Kirchhoff equation. Minus IR minus L di dt minus Q over C equals 0. I, of course, is dq dt, leading to second derivative of Q with respect to time, plus R over L, if we divide everything through by L, R over L dq dt, that's the I, 1 over LC, Q equals 0. So now the solution to the charge at any given time has different forms depending on how big the resistor is. If the resistor is really small, I mean if it's 0, is what we've already discussed. But it's never quite 0. If it's small, we call it underdamped. If large, we call it overdamped. You might remember SHM and the shock absorber analogy I gave then. It's the same idea. For the underdamped case, we end up with this kind of a result, sometimes called a ringing circuit because of the way it sounds. And so we have this oscillation that's diminishing. in a very particular way. Whether voltage or current, doesn't, either one. So what is this new angular frequency? Well, the new angular frequency, it's reduced from square root of 1 over LC by this other factor, r squared over 4L squared. Now when r approaches 0, no resistance in the circuit, then the new angular frequency is the same as the original. But when you add r, and again, you can't help it because all conductors have some resistance, the angular frequency is reduced. And when it's this value, when r squared equals 4L over C, you can do the algebra, makes this whole thing go to 0. It no longer oscillates, and then it's said to be critically damped. Well, that will conclude this course in AP Physics. I hope that you've learned a lot. Certainly if you've hung with this from beginning to end, certainly you know a lot more about physics now than you did then. And may you continue to study the laws of nature and be inquisitive beyond the requirements of this course, and live long and prosper.